And welcome to some exciting math practice. So this slide looks like the other one, just for our introduction of electromagnetic waves. But today we're just going to focus on doing some math. Again, this shouldn't be overly complicated, particularly if you use your Desmos calculator, because the only tricky thing with this is using some scientific notation. So we'll be using some exponents. So we're just simply solving some math problems involving wavelength, frequency, speed, and velocity. You have done these before when we worked on sound waves. And so again, the formulas are going to be exactly the same as we've used previously. There's no new formulas. So this shouldn't be overly complicated, but we do want to go through a few examples and know that you're going to need to be able to do these to answer some questions as a follow-up and to get a decent grade on your first quiz for this unit, because I'll have a couple of questions like this. So as a reminder, when we calculate these, we're going to be using the formula down here at the bottom. V equals lambda times F. Again, remember, lambda is the wavelength and F is for frequency. V is going to be for velocity or speed. So again, if you see the word speed, we can substitute that in for V. With electromagnetic waves, again, they're going to be traveling at, unless you're told otherwise, it's going to be 3.0 times 10 to the 8th. And so this is where I was saying, using your Desmos calculator, make sure that you're typing in the exponent correctly. And then again, if you need help about how to do that, please ask. It's pretty simple, but you just got to make sure you're pressing the right buttons on the calculator. Okay, so if we see any of the following waves, it's a radio wave, microwave, infrared, any of the Martian, Venus, X-ray, gun rays, our speed is going to be 3.0 times 10 to the 8th. So that's always going to be substituted in for V. And again, sometimes electromagnetic waves don't travel at that speed if they're not in a vacuum. So this is in a vacuum. We're going to work through 3 examples. I would encourage you to write these out, at least be able to solve them, or at least know how to solve them. Because again, you're going to have some that you're going to need to do in your own here in a moment. So the first one says the AM radio band, if you still ever actually listened to the radio, it goes from 5.4 times 10 to the 5th hertz. Whoops, we lost it, to 1.7 times 10 to the 6 hertz. And actually on your radio dial, if you look at the AM stations, it goes from 540 to like 1700, and it's 540 kilohertz. So that's usually what we see on there. But again, it's 5.4 times 10 to the 5th and 1.7 times 10 to the 6th, asking us what wavelengths would these two numbers correspond to, basically. So we know the range from the lowest frequency to the highest frequency. How does that correspond to the wavelengths that go along with that? So you got 2 problems to solve here. So on the left-hand side, we know the velocity, again, because it's an electromagnetic wave, so it's 3.0 times 10 to the 8th. And we know the frequency, which is 5.4 times 10 to the 5th hertz. Likewise, for the second wave, we've got the same velocity, which is 3.0 times 10 to the 8th, and the frequency in this one is given to us. So we're given a velocity, we're given a frequency, and what we need to do is to find the wavelength. So we take our original formula, we need to get wavelength by itself, which means frequency, the F needs to go to the other side. So our rearranged formula is going to look like this. So to get our answers, we simply need to take that velocity and divide it by that frequency. You could put this into your Desmos calculator. So for the first one, put it in, divide the 2 numbers. For the second one, do the same thing, divide the 2 numbers, and then the answer that it spits out should be our answer to the question. So for the 5.4 times 10 to the 5th hertz, we would get a wavelength of approximately 555 meters. If you did this in scientific notation, we would round that to 5.6 times 10 to the 2nd power. Again, when you do scientific notation, we always do times 10. And so these 2 numbers are equivalent, because basically 5.6 times 10 times 10 is going to be 560, or approximately 555. The other equation, again, how we set it up is the same way. The only thing that was different was the frequency that we had. And so because we got a different frequency, we end up with a different wavelength. And again, the calculator, when you put it in, should give you about 176, or in scientific notation, we would round that to 1.8 times 10 to the 2nd. Okay. So again, the math is, we're using the same formulas we had before. The only little curveball that we have here is using the scientific notation, but the calculator should take care of that for us. All right. Example number 2, kind of going in the reverse. If we know the wavelength and want to find the frequency, very similar to what we just had on the previous problem. So what do we know? We've got a formula, V equals lambda times F. But in this case, we're trying to solve for frequency. So I need to get this F by itself, just like we did before. When I move lambda to the other side, I have to divide it out. So in other words, since it's lambda times F, I have to untimes it. I have to unmultiply. I have to divide it to get it to go away. And if I divide it out on the right side, I have to divide it out on the left side. So this first equation becomes the second equation, simply by moving the lambda to the other side. So what do we know? We know what lambda is because it's 1 kilometer. And here's a little tricky thing on this one. To do the math on this one, because velocity is in meters per second, then our units have to be in meters and have to be in seconds. So this is a wavelength of 1 kilometer. So you wouldn't want to substitute 1 in for the wavelength because it needs to be in meters. So you'll notice that down here, our wavelength is actually 1,000 meters. And our velocity is 3.0 times 10 to the 8th. So again, if that's in meters, this has to be in meters and likewise. All right. If you'd have left this at kilometers, you actually can, but you would have had to change this to kilometers as well, and that becomes a little bit complicated. All right. So we plug our numbers in. Again, it's velocity divided by wavelength. So we know our velocity. We have it written over here. We know our wavelength. We divide those two together, stick that in Desmos in your calculator, and it's going to give you an answer of 300,000 hertz. If you put this in scientific notation, again, scientific notation is always going to be, the first part of scientific notation is always going to be between 1.0 and 9.9. In other words, you're only going to have one number in front of a decimal. So to turn this into scientific notation, we would put the decimal after the 3 so that we would have 3.0. And then we would need to say how many times would I have to multiply 3.0 times 10 to get it back to this number. And the kind of the easy thing to do, if you can see my arrow, is if I put the decimal here, every time I multiply by 10, it would move the decimal over here. In other words, 3 times 10 is going to make it 30. 30 times 10 would be 300, and so forth and so forth and so forth. So if you count how many times you would need to move the decimal to get it all the way back to the end, that number is your exponent, because that tells you how many times you would multiply times 10. So 3.0, 1, 2, 3, 4, 5, and that's where the 5 comes from on that. So these two numbers are equivalent. That's the main thing to understand. 300,000 is the same thing as 3.0 times 10 to the 5th, right? And then finally, our last example is, it really doesn't use this formula over here. It uses one of our formulas for first semester. How long does it take for light from the sun to reach the earth if the sun is 1.5 times 10 to the 11th meters away? So in this one, we need to use our velocity distance time formula. And so we're given, again, we know the velocity of light is going to be 3.0 times 10 to the 8th. This is actually on your reference sheet. If you haven't looked at that yet, you should. It uses the symbol c for the speed of light. You may have seen that in the equation, Einstein's famous equation, E equals mc squared. In that case, that equation c is the speed of light. So it's 3.0 times 10 to the 8th. So you don't have to memorize this. It's on your reference sheet. So we're solving for t. This is the formula we have on a reference sheet. Velocity is distance divided by time, like miles per hour or meters per second. But since we're trying to solve for time, we need to rearrange the equation. This is one of those kind of weird ones because time is on the bottom. You could make your triangle and figure this one out pretty well, because if you made a VDT triangle, the D would be on the top. So when you solve for T, basically D is still going to be on the top, but D and V they can be switched places on this. So to rearrange your formula, T equals D over V, or you could plug your numbers in and rearrange after that. But then we just stick it in the calculator because we know our distance, we know our velocity. So we put those in the calculator, 1.5 times 10 to the 11th, and divide that by 3.0 times 10 to the 8th. And we get an answer of about 500 seconds, which is around 8 minutes. It's the amount of time it takes for light to travel from the sun to the earth. Right. So there's 3 example problems. Again, I would encourage you, hopefully, that you have written those down, because now you're about to move on to some practice to see if you can do these things. And again, if you need to rewind, go back and check on how to do some of these, please do so. And always, always, always come to me for help if you need some.